Thanks for the introduction, and thanks for coming despite the tempting offers to go to the Kafka Museum. I'm sure you can go afterwards. So this talk is about JavaScript, and I guess everybody here agrees that JavaScript is an unusual language. And one of the reasons why it's so unusual is the way it has been created. So as Brendan Ike told us Tuesday in his keynote, he was hired by Netscape to create a new language for the web. And there was a little bit of fine print in this offer, namely that he had only 10 days. And even though he's a great language designer, you can imagine that if you design and implement a new language in 10 days, you make some mistakes. And because JavaScript has to be backward compatible, these mistakes prevail until today. A nice way to illustrate some of the design issues in JavaScript is to look at these two books. So the book on the left describes the full JavaScript language, and it takes more than 1,000 pages. And the book on the right describes the so-called good parts of JavaScript, and takes only 150 pages. Now, if this would be it, we could just stop here and ignore JavaScript. But JavaScript is also unusual in another way, namely because it's very popular. So this graph shows how many new projects created at GitHub primarily use a particular programming language. And as you can see, JavaScript has become the most popular language a couple of years ago, and actually it's still the most popular language today. So because JavaScript is so unusual, and because it's so popular, the PL community should not ignore it. And this year's ECOOP program shows that the PL community doesn't. And instead, we should try to understand how this language is used and why it's used in a particular way and how we can improve it. And that's what we try to do in this paper. So in this paper, we look at one of the most unusual language features of JavaScript, which is type coercions. A type coercion is an implicit conversion of a value of one type into a value of another type. It allows you to write very concise code because you don't have to explicitly convert values. So instead, you can just use a value of some type in the context in which you actually need a value of another type. And then the runtime or the compiler will implicitly convert it for you. JavaScript is not the only language that has type coercions. Many other languages have them. For example, in Java, you have implicit upcasts to a supertype. Or in C and Python, you have implicit conversions of numeric values between integer and float. But if you look at the language, or if you look at the spectrum of languages with respect to type coercions, then JavaScript has a very extreme position here because it makes very heavy use of type coercions. And as you might have heard elsewhere, JavaScript is infamous for being, for having semantics of type coercions that are pretty complex and sometimes very confusing. And I just want to show you a few examples. So here, for example, we are comparing booleans with strings. And I don't know what you expect what happens, but what happens in JavaScript is that the first evaluates to false, and the second evaluates to true, which may be surprising. It's not surprising if you know the rules, but if you don't know the rules exactly, which most developers probably do, then it's a bit surprising. The reason why this happens here is that when you compare a Boolean and a string, then the string gets coerced to a number, and then the comparison happens. So in the first example, false coerces to nan, not a number, and nan is not the same as false, so the comparison is false. But in the second example, the 0 string converts to the 0 number, and this is treated as equal to false, which is why the second comparison is true. Another example is this one, where we're comparing strings. So in JavaScript, we have primitive strings and object strings, and we are comparing an object string with a primitive string with an object string, and two object strings. So what you would probably expect is that both, or all three examples are either true or false. But what actually happens is that the first two are true, but the last one is false, which unfortunately implies that equality is not transitive. Just to show you some more examples, so here we are applying the arithmetic leftshift operator to an array and strings. And I could explain you why you get these values, but instead of doing that, let's just ask the question, should these be valid at all? So in a good language, do you want to have these operations? Probably not. So because of all these confusing examples, and there are many more of them, it is commonly assumed that coercions are not used very often in JavaScript, even though they exist, and that if they are used, they are error-prone. And of course, people assume that coercions make the code hard to read because they are so confusing, right? So now in this work, we are challenging these assumptions by asking, really, is that really the case? And by empirically studying how JavaScript's coercions are used in practice. Okay, so why does the PL community need such a study? So what can the PL community learn from studying how a language is used in practice? I think in general there are many things you can learn, but for this particular study, we believe that it enables more informed decisions for three groups of people. First, for designers of program analyses, because whenever you design a program analysis for JavaScript, you have to decide whether you want to consider coercions and which ones you want to consider if you don't consider all of them. And maybe you're also thinking about designing an analysis that looks for bugs caused by coercions, and you might be interested in whether these bugs actually exist in practice. It's also interesting for people who work on language subsets. So at ECOOP, there are a couple of talks on subsets of JavaScript. And an important question is, of course, which parts of JavaScript do you include and which parts do you forbid? And you want to know if you forbid a particular feature, for example, some kinds of type coercions, how much real code would you break by doing that? And finally, it's interesting for designers of future languages, because in every language, at some point, you have to decide whether you want to have type coercions or not. And since JavaScript makes this extreme decision to have lots of type coercions, it's a good case, it's a good candidate to look at to decide which ones you probably want to have and which ones you may not want to have. Okay, so in order to understand how JavaScript coercions are used in practice, we looked at both JavaScript applications in the web. So we looked at the top 100 websites according to the Alexa ranking of the most popular pages. And we looked at the two most popular benchmark suites, the Octane benchmarks and the SunSpider benchmarks. So for each of these programs, we applied a dynamic analysis, where we dynamically analyze all operations in the program where a coercion may occur. And then, so for example, for binary equals operation, we check which types and which values we see each time this operation is executed, record this, and then based on all these data, we perform the actual analysis. The dynamic analysis is based on Jalangi, which is a framework for dynamic analysis in JavaScript that works through source-to-source transformation. So in total, we looked into 132 programs, about 140 million runtime events, and these events come from 320,000 code locations. So it's a pretty large-scale study. Okay, so let's look at our first question that we have, and that is how prevalent are coercions? So how often do coercions actually happen in practice? So to address that question, we defined a new measure, which is the percentage of function executions that have at least one coercion among all function executions. So if we measure that and we take the average over all programs, we find that 80% of all function executions have at least one coercion. So this basically shows that coercions happen very, very often because they happen in 80% of all function executions. And even if we look at the range for different programs, then we see that even programs that do not have that many coercions still have 20% of all function executions with at least one coercion. So the conclusion from these results is that coercions are very prevalent, so they exist in practice. And even for programs that don't have that many, they are certainly non-negligible.
Does that include transitive calls?
It does not. So when I say in the function execution, I mean we are excluding the calls. Yeah, yeah. Otherwise, the numbers would be skewed. But yeah. Okay, so now we have lots of coercions. The next question is, what are they actually used for? So in this graph, the horizontal axis shows the different kinds of coercions that you can have in JavaScript. Not all of them, just the 10 most popular ones. And the vertical axis shows the percentage among all coercions that we observe for particular kinds of coercions. So the most popular here is to have an undefined value in a conditional, which is coerced into a Boolean, false. And that happens very often. For example, if you get some value from somewhere stored in some variable, for example, x, and then you want to check whether x is actually defined by just saying if x. The second most popular is that the negation operator is applied to a number, and this can, for example, happen in this kind of code, and it seems to be pretty popular in JavaScript. So the main conclusion here is that there are various different kinds of coercions. It's not just one that happens all the time, but there are many. But the most prevalent cause why you have coercions are conditionals and operations like logical negation that you typically use in conditionals. So to better understand what coercions are used for, we also manually inspected some code locations. So we randomly sampled 30 code locations. Inspecting those is non-trivial because most code in the web is obfuscated and it's not so easy to understand what it's actually doing. But so as far as we could figure out of these 30, 10 use a coercion to check if some value is defined before using it. We found a few cases where minified code uses not 0 or not 1 as a shorter way to say true and false. We also found a couple of cases where coercions are used to check if an optional argument is defined. So in JavaScript, there's no function overloading, so developers have to instead check if a function argument is defined. And finally, we found a few occurrences of a pretty common initialization pattern where you have this code that you see in the corner, where some counter-like variable x is initialized to 0 if it's undefined, and afterwards, if you execute this code, it always gets incremented. And this leads to a coercion because undefined and the bitwise OR with 0 needs to coerce undefined into 0. So besides implicit conversions or coercions, there are also explicit type conversions in JavaScript, and we were wondering whether developers use those. So for example, instead of implicitly converting a Boolean, as we've seen before, you could also say Boolean of and then some value, and then you make the type conversion explicit. And well, as you can see from the numbers, we found about 5.5 implicit conversions, but only 20,000 explicit conversions in all the programs we analyzed. That basically means that explicit conversions are not very popular, and developers seem to prefer the more concise way to write code by using implicit conversions. Okay, so now we know that coercions happen very often and what they are used for. The next question is whether coercions are error-prone. So do some of these uses lead to bugs in the program? To address that question, we came up with a classification of coercions, so that enables us to distinguish between different situations in which a coercion may occur. So we basically went through the specification and looked at all situations where coercions can happen in JavaScript. Broadly speaking, coercions can happen in conditionals, in unary operations, and in binary operations. And we further divided these groups into subgroups. This categorization is done such that each class can be classified as either likely harmless or potentially harmful. So we made this classification based on guidelines and books that tell you which kind of coercions you should probably avoid because they are harmful, based on the similarity of the semantics of JavaScript to other languages, because we assume that developers come from some other languages and may be familiar with some semantics, but may be surprised about others. And finally, it's based on documented experience of developers, for example, blog entries and Stack Overflow questions where people say, well, this kind of coercion causes trouble. So nevertheless, it's not a clear-cut classification, which is why we say potentially harmful and likely harmless, but it's the best we could come up with. So for example, we classify a conditional that uses a wrapped primitive as potentially harmful. So in JavaScript, you have primitives and wrapped primitives. For example, you can wrap the Boolean value false into a Boolean object. And then if you use that Boolean object in a conditional, it evaluates to true, even though the actual value that is wrapped is false, because every object coerces to true. And well, as you can see, it's a bit surprising, so probably developers may not be aware of this, so we classify this as potentially harmful. Another harmful coercion is concatenation of undefined with a string. So since plus is overloaded, it can mean addition and string concatenation. And if you declare a variable, for example s, but you don't initialize it, and then append a string with plus equals, what you will get is a string that contains undefined, because the undefined value s is coerced into the string undefined before the concatenation is done. So this is also potentially harmful, and what we also classify as potentially harmful is comparisons with the equal or not equal operator if the two values have different types. And the reason here is that the semantics for this comparison is very complex, so there's a long list of rules that explains what happens in this case, and probably most developers do not fully understand the semantics. Okay, so now, based on this classification, we can measure how many coercions are potentially harmful. And we did this for all the programs we looked at, and in total, or on average, we find that about 1%, so 1.15% of all coercions that happen are potentially harmful. That means most coercions are harmless, and for most coercions, developers seem to know what they are doing. So in the graph, you see the 10 programs with the highest percentage of potentially harmful coercions. So there are 3 outliers. The first 3 are rather small benchmarks from the SunSpider benchmark suite. And then all the others are programs that have less than 12% potentially harmful coercions. And as I said, the overall average is 1.15%. which basically means that most coercions are harmless, even though there are some programs where you have lots of harmful ones. So the next question is, among these potentially harmful coercions, what kinds of coercions are the most popular? So we did the same experiment as before, but now just focusing on the potentially harmful ones. So basically, there are two main reasons why JavaScript has potentially harmful coercions. One is related to the non-strict equality operator, which has pretty confusing semantics, and I'll get back to that in a few minutes. And the other is that it's very easy in JavaScript to have an undefined value propagate through the program, and then you may use this undefined value in some operation where you don't expect it, like a string concatenation, or maybe a relational operator, and then you get results that are usually not expected. So we also inspected some of these potentially harmful coercions to further understand what they are doing. And so out of 30 code locations that we looked at, we believe that 22 are probably correct. So they do something unusual, but it's probably correct. We found one very clear bug, so where we're sure that it's a bug. 3 cases that may be buggy, but it's not fully clear to us. And 4 where we just didn't understand what's going on because the code was obfuscated. So for the 22 probably correct ones, what's the reason? So 10 of those were cases where a number is represented in a string, which is suggested not to do because all arithmetic operations have the usual meaning, but plus means string concatenation if you apply it to a string, even though the string is supposed to represent a number, which may lead to surprises. But in those 10 cases, plus was not applied to the value, so this is why we say it's correct. Then we had cases where string is concatenated to undefined, but it actually didn't do any harm in those cases because the string was used in a way where the undefined didn't really matter. And then we had 2 cases where 2 different types are compared with the equals operator, which is always false, but in this case, it didn't really lead to any important misbehavior. Let's look at the one bug. So we found this on a Chinese news site that encodes the fact that you have a particular version of the Flash player installed in your browser as a bit pattern in a variable called m. And then it wants to use that code to check whether a particular bit pattern is in this value m. And I guess the developers assumed that the bitwise AND has precedence over equality, but this is not true. It's actually equality has precedence over bitwise AND, which means that this code always compares m to false, which means this check is always false, and it just cannot be true. We checked again at this, whether they fixed this, and 3 days after we found this, they had actually changed it. So the developers apparently also realized that it was not correct. But despite this example, so the overall conclusion is that most coercions are harmless. So there are some examples where they actually lead to bugs like this, but it's rather the exception and not the rule. Okay, so now the final question that we have is whether coercions harm code understandability. And now there are many ways in which coercions could harm code understandability. In this study, we looked into 2 ways and performed 2 experiments to see if they harm code understandability in this particular way. The first is polymorphism of code locations. So because you have a coercion, it may happen that a single code location may perform a different coercion at different times that the code location is executed. So if different types arrive, different coercions may happen, and this may be confusing for developers. So to see whether this is the case or not, we looked at all locations where you have at least one coercion, and we looked at the number of different types that are used at this code location. And this graph shows how many different types you see in particular percentages of code locations. And what you basically see here is that for most code locations, it's 87%, there's just a single type, which means that the code locations are monomorphic and there's no problem because of polymorphism. For the polymorphic code locations, we looked into what are the reasons here, and what we found is that the main reason is that these code locations, at these code locations you either see undefined or some other type, or a logical negation where that happens, which basically means it's places where someone checks whether something is defined or not. And these are cases where developers expect polymorphism because they explicitly check whether it's this or that. So the bottom line here is that most locations are monomorphic, so this is not a reason for for harming the code understandability, and that most polymorphism that we see is expected. Another reason why coercions may harm code understandability is the different semantics of strict and non-strict equality. So in JavaScript, you have two equality operators, or two kinds of equality operators. Strict equality, which is triple equals, and this is only equal if both operands have the same type. So this is what you would expect, well, what you get with equal in Java, more or less. And then there's non-strict equality, so double equals, which first applies coercions, if possible, to see if it can make the two values equal, and then does the equality check. And because the semantics of non-strict equality are pretty complex, the common advice is to avoid them and to instead use only strict equality. So now, do developers follow this advice? Well, not really. So most of the coercions that you see, or no, most of the cases where you see equality checks actually are non-strict, but there are also strict ones. So maybe developers do this on purpose. So if you know that the two operands may have different types, then it could be a reason to use non-strict equality, assuming that you understand the semantics. So we looked at how many different types we find for these equality checks. And interestingly, both for strict and for non-strict equality checks, almost always both operands are of the same type. This basically means there is no good reason to use non-strict equality, but instead most of these code locations should probably be refactored into strict equality checks just to make them easier to understand. And given that they use non-strict equality, they are actually harder to understand because if you read the code, you always have to reason about the coercions that could happen. So this is a case where the confusing semantics of the two equality operators harm the code understandability, and there's a potential to refactor some of these code locations into strict checks. Good, so as all empirical studies, there are some threats to the validity of the conclusions we draw. The most important threat is probably that we apply dynamic analysis, so we underestimate the behavior of programs in various ways. For example, the degree of polymorphism that I've shown you is an underestimate because we don't know how many different types could be seen at a particular code location. Another potential problem is that the classification into likely harmless and potentially harmful is to some degree subjective. The good news is that all our raw data is available, so if you want to just redo the experiments with a different classification, you're welcome to do so. It's not clear whether the programs we looked at are representative for the whole universe of JavaScript programs. We try to reduce this potential bias by looking at a wide spectrum of popular benchmarks and at a wide spectrum of popular websites and benchmark suites that are used. And finally, everything we do is for JavaScript only, so any conclusion that you might draw for other languages has to be taken with a grain of salt. There's some related work, of course. So there have been studies on languages before this one. In particular, there was one by Donald Knuth in 1971 who studied how Fortran is used in practice. And more recently, there have been pieces of work to see how Java is used in practice, and also some work on JavaScript, but that work did not look into type coercions. And the other stream of related work is approaches to analyze and restrict the usage of types. For example, there has been work on type inference and type checking. And actually, some of this work makes assumptions about type coercions that we show to be false. So some of these analyses assume that type coercions do not exist, or they assume that all type coercions are an error, both of which we show to be not the case. So in conclusion, I've presented the first in-depth study of type coercions in JavaScript, and there are three main conclusions that we draw. The first is coercions are widely used, so they exist and they should not be ignored. The second is that most coercions are harmless, so despite popular belief that they are pretty confusing, which they can be, in practice, it seems to be not such a big problem. And finally, we find that they sometimes at least harm code understandability because of these two different equality checks that you have in JavaScript. So some implications for future research. One implication is that static analysis, or actually every analysis for JavaScript, but in particular static analysis, must consider coercions, otherwise the analysis won't run on any realistic program. Another implication for future languages and subsets of JavaScript is that you probably want to disallow some coercions, in particular those that we classify as potentially harmful. And by doing this, you wouldn't break too much code because only 1% of all coercions are of this kind. And finally, there's potential for future work and to refactor equality checks from non-strict checks into strict checks. And that's the end of my talk. So thanks for your attention, and I'll be happy to take any questions.
Hi, and thanks for the talk. Does the portfolio of programs you have analyzed includes programs that are the result of compiling other languages to JavaScript? So I'm not talking about minifying, but really other languages that compile to JavaScript, because these, the conversions could be the result of the compiler abusing some of the semantics to implement efficiently some of its semantics.
Yeah, that's a good point. That's another threat to the validity that I didn't mention on the slides. But yeah, so the study certainly includes some generated code. Because we had no easy way to distinguish this, we just analyzed everything we found in the web, basically. Yeah.
Hi, so very good work. The classification you made for harmful coercions is very useful for like type checkers for JavaScript, because they can try to remove these, ban these at compile time. So one particular thing I did not quite agree with in your study was, or maybe you have a different answer here, is that sometimes double equal to, like the non-strict equality, is better. For example, when you're comparing with null or undefined, that's like a very common pattern.
Let me just go back to the classification then. Yeah, so if you compare something with undefined or null, we classify it as likely harmless, because that's something that happens very often. And we don't think it's a problem because developers know what they do. So we only classify it as potentially harmful if it's two different types, but none of them is undefined or null.
So did you find any? This is sometimes preferred over existence checks when you have like different kinds of types coming in, because the thing you're checking may not just be undefined, but in fact
it may be an empty string
or some other things.
Yeah.
So did you kind of try to look at the existence checks and kind of differentiate them into things that were going to be undefined versus other kinds of types that were flowing in? For example, numbers or something.
It's an interesting question. So we didn't do that, but I think you could very easily do based on our data. So I think it would may take 10, 15 minutes maybe to rerun the experiments, and then I can give you an answer. Yeah.
Also, when you were saying that it's difficult to manually inspect some of these things, have you heard of JS Nice?
Yeah, that's what we actually use to at least understand a bit of what is happening. But it's useful. It's useful, but it doesn't help with all code, obviously. Okay. Yeah.
So when you were comparing the number of
Where are you? Oh.
the number of implicit and explicit coercions, and also when you were comparing the number of strict versus non-strict equalities, were those static counts or dynamic counts?
So for all experiments, we did static and dynamic counts, but in the talk, I just showed one of them.
Okay, which ones were those?
So this was dynamic counts.
I see.
And the other one you asked about was what?
The other one, well, I mean, we can talk about this one for now.
Yeah.
So do you expect that maybe this this asymmetry, maybe because programmers are reluctant to use but what they may imagine maybe a more expensive explicit coercion in hot code, and therefore these 20,407 explicit conversions may be in infrequently executed code, and that in fact programmers are aware of these coercions, are just reluctant to use them?
So I think an explicit coercion is not necessarily more expensive.
Oh, I know you know that. Maybe they don't. That's what I'm saying.
I actually think it can be cheaper because the JIT engine doesn't have to try out what to do. It knows exactly what it has to do. So I think if you're concerned about runtime, you may even want to use some explicit conversions.
Right. I'm just not sure whether that's common knowledge among JavaScript programmers.
Probably not. Yeah.
Right. Okay. And yeah, similar question for the wrote it down for the strict versus non-strict equality, but it's the same question. You don't need to answer it again. But just wondering.
Oh, whether it's dynamic or static?
Yes.
Let me check it. My notes no. I don't know where I had.
Because numbers were already neck and neck, basically. I think there was a slide before. Yes.
Oh, this one.
Yes.
This is also dynamic.
I see. Okay.
Yeah.
Thank you.
So I think coercions are an interesting feature of JavaScript insofar as they're one where we would expect that more experienced programmers know both how to and to avoid them, and probably, so with this classification you've made, probably those are the ones they would use. So I wonder if you saw different, like a differing range of patterns on, you know, the Googles and Gmails and Bings of the world than on the, you know, various porn sites and other things that are on the top 100 list.
Let me think. So we have this. I don't think we have it here. So in the paper we have the top. Well, the pages with the most potentially harmful coercions and with the least percentage of potentially harmful coercions. And I remember there were some porn sites. I don't remember where they were exactly, but if you're curious, you can just look it up.
Last question. Have you compared minified and non-minified versions of the same programs for implicit coercions in case minifiers are taking advantage of extra information about JavaScript that programmers can't hold in their heads to generate more obfuscated code, for example?
No, we haven't, but I know that minification certainly influences the coercion. So there was this one example with not 0 and not 1, which is to say true and false and save a few characters. Yeah, but it's a good idea. We didn't do that. Yeah.